So in this video, I'm going to expand on this idea of confidence intervals and the different effects different pieces have on confidence intervals. So specifically, I'm going to look at what does changing your percent confidence, what does that do to my confidence interval, and also changing the sample size, okay? So changing the percent confidence. So in short, I'll explain what the changes are, and then I'll explain why does that make sense. So when you change the percent confidence, okay, if you go to a bigger confidence, so you increase your confidence, say from a 95% to a 99, you're going to end up with a bigger interval. That's assuming everything else is relatively staying the same. When you talk about all these things together, it gets quite messy. If you decrease your confidence, so you go from a 95 to a 90%, you're going to have a smaller interval. And we'll talk about why this makes sense kind of mathematically and a little bit non-mathematically. So percent confidence, you increase your confidence, you're going to increase the size of your interval. So your interval is going to get wider, okay? Margin of error is going to get bigger. You decrease your confidence, interval is going to get smaller. Your margin of error is going to get smaller. So think about it like this. If I had created, say, two targets on my paper, say a target this size and a target this size, and I held this paper up and you had a dart and I said, hey, you're going to throw a dart to hit one of these targets, okay? And I said, which one do you feel more confident in? You could do the smaller one or the bigger one. Which one do you feel more confident that you could throw a dart and you could hit? Well, if you pick this right one, your confidence is probably going to be much larger than your confidence in your ability to hit the smaller interval. So as you try and throw at a bigger target, hence a bigger interval, you have much, much more confidence. When you go to the smaller interval, you're going to have a little bit smaller confidence. So that's kind of how I think about how does confidence affect everything here, a non-mathematical approach. If you want to think about it in a mathematical approach, let's look at the 1 proportion z interval. So you're looking at this formula right here. Let me write it all out. 1 proportion z interval. When we're talking about confidence, we're really talking about, in this formula, the z star piece, the z star piece. Now, we pick our z star based on our confidence. So remember, the typical ones we work with is we deal with 90% confidence, 95% confidence, or 99% confidence. Of course, you can do others, but those are just the common 3 we use. Now, this z star is going to act like a multiplier here. It's this number multiplied whatever you get from the square root, and that's what it creates as your margin of error. So it's a multiplier here. So the bigger this number gets, the bigger this overall number gets. Okay, the smaller this number gets, the smaller this overall number gets. So the bigger your z star, the bigger your margin of error. The smaller your z star, the smaller your margin of error. If we think about our z stars, when we're at 90%, 95, and 99, when we're at 90%, our multiplier is 1.645. That's what we plug in for z star. When we're at 95%, our multiplier is 1.96. And we're at 99%, we're at 2.576. So as our confidence gets bigger, our z star gets bigger. So our multiplier gets bigger. So mathematically, it makes sense. As you get a bigger confidence, you're going to end up with a bigger interval. As you go to a smaller confidence, your multiplier is smaller, so you get a smaller interval. Okay? So that's changing the percent confidence and how that affects the confidence interval. Next, we have changing the sample size. Changing the sample size. Now, these are going to work inversely. If you do a bigger sample size, you're going to end up with a smaller interval. If you have a smaller sample size, you're going to end up with a bigger interval. Now, again, when I'm saying smaller interval and bigger interval, I'm talking about the margin of error, the kind of size of your interval. Big intervals, small intervals. You get the idea. So let's talk about why this makes sense non-mathematically, and then we'll look why it makes sense mathematically. So if you get a bigger sample size, okay, that means you're learning more about your population, okay? So at the high school I teach at, we're talking about 1,700 students. If I sample only 20 students, which is very, very small out of 1,700, I really don't know a whole lot about my population. So if I'm trying to make an interval, I'm going to make it pretty big because, gosh darn it, I don't know a whole lot. Where if I increase my sample size, and I have a sample size of, 200 students, whatever, I know I'm violating some assumptions there, but just go with it. If I do a sample size of 200, I know a lot more about my population. Even if I did a sample size of 1,000, man, I know so much about my population. I should be able to make a much, much more smaller and precise interval because I know a lot more information. There's no reason in giving a monster interval. If I know a lot of information, I'm going to be able to say, I'm pretty sure a population proportion or population mean is inside this interval. And it works the opposite way. If I don't really know anything, I have a small sample size, I'm going to have to use a big interval to be like, you know what, I think our population proportions from here to there. That's kind of the non-mathematical approach to that. The mathematical approach to why increasing your sample size is going to decrease the size of your interval and vice versa is, again, let's look at the formula here. And you can look at the one proportion z intervals. You can look at the one sample t intervals, either or. They both have the same thing. When you look at where your sample size is, that's n, it's on the bottom of a fraction here. It's on the bottom of the fraction. So when it's all said and done, you could say, hey, this is some number over the square root of n. That's fine. If you just want to even think of it more plainly, you just have a fraction with your sample size on the bottom, okay? A fraction with your sample size on the bottom. So if I'm comparing like 1 over 10, which is 0.1, and I increase that size of the bottom of my fraction. I increase the size of the bottom of my fraction, which would be the same as increasing my sample size. Instead of 1 over 10, I increase this to 1 over 100. I'm now 0.01. So as the bottom of my fraction gets bigger, the overall number gets smaller, okay? As the denominator of my fraction gets bigger, from 10 to 100, my overall number gets smaller. So it works the same way here with this fraction. As you increase your sample size, this number is going to get smaller and smaller and smaller. Therefore, your margin of error gets smaller and smaller and smaller. Therefore, your interval is smaller. Works the opposite there as well. As you get a smaller sample size, so if I make this number smaller, smaller, and smaller, my interval is going to get bigger and bigger and bigger. I might have flipped my words there, but pay attention to what I have written down, maybe not what I'm saying. It's sometimes I get caught up on it. So as your sample size gets bigger, your interval is going to get smaller. As your sample size gets smaller, your interval will get bigger. Okay, that's a quick summary of the two major pieces that are going to affect our confidence intervals: your percent confidence and changing your sample size. I talked about these in terms of the one proportion z intervals. The same rules apply if you're doing, intervals for means as well. The same exact ideas. Again, this was effects on confidence intervals.